The Chandrashekar limit is a cosmic fork in the road for dying stars. It dictates their ultimate destiny. If the remnant core of a star, after it has shed its outer layers, has a mass less than about 1.4 times the mass of our Sun, it will settle down as a white dwarf. Our own Sun is headed for this fate. In about 5 billion years it will expand into a red giant, then shed its outer layers, leaving behind a dense, hot core, a white dwarf. This stellar ember will gradually cool down over billions more years, eventually becoming a cold, dark black dwarf. It's a relatively peaceful end for stars like ours. But what happens if the star's core is more massive than the Chandrashekar limit? Electron degeneracy pressure isn't strong enough to stop gravity's crush. The core collapses catastrophically. If a white dwarf in a binary system siphons enough material from its companion star to push its own mass over the Chandrashekar limit, it triggers a runaway nuclear fusion reaction. This results in a spectacular explosion known as a Type Ia supernova. These supernovae are incredibly bright, often outshining their entire host galaxy for a short time. They are crucial cosmic events, scattering heavy elements synthesized during the explosion far out into space. Elements that can become part of new stars, new planets, and perhaps even new life. For stars that are initially much more massive than our Sun, say 8 to 20 times its mass, their cores will naturally exceed the Chandrashekar limit when they run out of fuel. Their collapse doesn't stop at the white dwarf stage. The inward crush is so intense that electrons and protons are forced together to form neutrons. This creates an even more exotic state of matter and a new kind of pressure neutron degeneracy pressure. If this pressure is sufficient to halt the collapse, the result is an incredibly dense object called a neutron star. Imagine a star more massive than our Sun squeezed into a ball just a few miles across, a city-sized stellar remnant. These can spin rapidly, emitting beams of radiation, which we sometimes observe as pulsars. And what if the collapsing core is even more massive? Say from a star that was originally more than 20 or 25 times the mass of our Sun. In this scenario, even neutron degeneracy pressure cannot withstand the overwhelming force of gravity. There is no known force in the universe that can stop the collapse. The core continues to shrink, crushing itself down to an infinitely small point, a singularity. This creates a region of space-time from which nothing, not even light, can escape, a black hole. The Chandrashekar limit, therefore, is not just about white dwarfs. It's the first crucial gateway to understanding these even more extreme and mysterious objects that populate our universe. It defines the boundary where one kind of